Hello everyone, this is Mohana, Assistant Professor in the Department of Artificial Intelligence and Data Science. The subject is offered in the 4th year 7th semester students. The course code is 191ITV17 and today we are going to discuss about the learning technology in the subject of knowledge engineering. Today, we are going to discuss knowledge engineering, which is an important area of artificial intelligence. First, let's start with a simple question. How do humans solve problems? We rely on our knowledge, the facts we know, the rules we have learned, and our ability to apply reasoning. Now, the goal of knowledge engineering is to make machine do the same thing. It is the process of building intelligent systems that can store knowledge, reason about it, and make decisions like human expert. Now, let's understand knowledge engineering, one of the core areas of AI. AI is nothing but artificial intelligence. Definition: the knowledge engineering is the process of building intelligent systems that can use structured knowledge to reason, make decisions, and solve problems, just like human expert. It is not just about the storing data, but about capturing the expert knowledge and enabling the system to think with it. The major activities in knowledge engineering. The first one is knowledge acquisition. This is the starting point. It involves collecting knowledge from different sources, human experts, books, databases, experiments, or even direct observation. Example, a doctor's medical expertise can be acquired to build a diagnosis system. Knowledge representation. Once we acquire knowledge, we need to store it in a structured form so that a computer can use it. This can be done using rules, frames, semantic networks, logic, or ontologies. For example, instead of just writing, John is an expert in AI, we represent it formally so the mission can understand relationships between John and AI. Knowledge validation. Here we check the knowledge to ensure that it correct, consistent and reliable. Wrong knowledge will lead to wrong conclusions. So this step is very important. Knowledge inference. This is where reasoning happens. We design inference mechanism, inference engines so that the system can apply stored knowledge and draw conclusions. Example, if a patient has fever plus cough and the rules say these symptoms may include flu, the system can infer possible flu. Knowledge maintenance. Knowledge is not permanent, it evolves. Therefore, we must update and refine the knowledge base as new facts, discoveries, or rules become available. Example, in medicine, new diseases or treatments appear, so the system's knowledge base must be updated. Now that we know what knowledge engineering is, the next question is, why do we actually need knowledge engineering? What is its importance? There are several strong reasons. Capture and use human expertise. Human experts are valuable, but their knowledge is often limited to their experience and not easily accessible to everyone. Knowledge engineering allows us to capture expert knowledge and store it in a system so that it can be used by many people and even after the expert is unavailable. Solve complex problems. Many real world problems like medicine, medical diagnosis, business forecasting, or engineering design are too complex for ordinary computer programs. With knowledge engineering, systems can structure knowledge to reason through complex situations, just like a human expert. Consistency in decision making. Human decision making can vary. Two experts may give different answers. A knowledge-based systems provide consistent reasoning based on the same knowledge base and rules, avoiding bias and random variations. Efficiency and productivity. Once knowledge is captured and stored, it can be reused many times. This improves efficiency, speeds up decision making, and allows non-experts to benefit from expert level guidance. Example, a junior doctor using a medical expert system can quickly get support for diagnosis. Knowledge preservation. Human expertise is often lost when experts retire or leave. Knowledge engineering ensures long-term preservation of expertise in a structured, usable format. This way, knowledge continues to benefit future generations. Knowledge engineering is not just a theoretical concept. It has real practical applications across multiple domains. Let's look at some important areas where it is widely used. Engineering and manufacturing, used in design, quality control, fault diagnosis, and process optimization. Example, an expert system can detect faults in machinery and suggest a corrective actions. Medical diagnosis, one of the earliest and most famous applications. Knowledge-based systems help doctors in diagnosis, treatment planning, and drug prescriptions. Example, MISM, an expert system for infectious diseases. Robotics and automation. Robots use knowledge bases for planning, navigation, object recognition, and intelligent decision making. Example, industrial robots diagnosing mission errors and self-adjusting. Natural language processing, NLP. Knowledge engineering supports language understanding, translation, and chatbots. Example, virtual assistants like Siri, Alexa, or ChatGPT use structured knowledge for better responses. Law and legal advisory. Legal expert systems assist in interpreting laws, drafting documents, and case-based reasoning. Example, a legal advisory system suggesting applicable laws for a case. Agriculture helps farmers with crop disease diagnosis, soil analysis, and irrigation management. A knowledge system recommending the best pesticide for a crop disease. Finance and business, used in credit risk analysis, fraud detection, investment planning, and business forecasting. Example, knowledge-based decision support systems in banking, education, and training. Intelligent tutoring systems adapt to learners' style and knowledge level. Example, personalized e-learning platforms using AI. Military and defense, used in strategic planning, surveillance, and threat detection. Example, knowledge-based defense systems for analyzing battlefield data. Now let's discuss learning technology, particularly in the context of agent decision and development. Definition, learning technology refers to the set of AI methods and computational tools that allow intelligent agents to automatically acquire, adapt, and improve their knowledge or behavior through experience and interaction with the environment. In simple words, instead of being limited to pre-programmed rules, agents equipped with the learning technology can learn from past actions, adjust strategies, and make better decisions over time. After understanding what learning technology is, the next question we should ask us, why do we actually need learning technology in agent design and development? There are several important reasons. First one is adaptability. Learning technology allows agents to adapt to new environments and unexpected changes. For example, a robot in a warehouse can adjust if the layout changes instead of requiring reprogramming. Second one, improved performance. As agents gain more experience, they learn from successes and mistakes, leading to better decision making and faster responses. Example, a self-driving car improves lane changing decisions as it learns from traffic patterns. Third one is autonomy. With learning ability, agents can function with minimal human intervention. They can make their own decisions instead of waiting for constant instructions. Fourth one, handling complex problems. Many problems like language understanding, medical diagnosis, or strategy planning are too complex for rule-based learning. Learning technology helps agents discover solutions that humans may not explicitly program. Fifth one, continuous improvement. Learning agents don't remain static. With every new interaction, they refine their strategies and continuously evolve to perform better. Sixth one, scalability. In large and dynamic environments, it is impossible to hard code every scenario. Learning technology scales easily, allowing agents to handle diverse situations without redesign. Seventh one, then the human-like intelligence. Ultimately, the goal of AI is to simulate human-like intelligence. Humans learn from expertise, experience, adapt, and improve. Learning technology enables agents to do the same. Now, let's look at the process of designing and developing intelligent agent using learning technology. This process can be broken down into several key phases. First one is the requirement specification and domain understanding. The first step is to clearly define what the agent should do and understand the domain of application. Example, if we are designing a medical diagnostic agent, we must define the scope, diseases, symptoms, treatments, and expected outputs. Rapid prototype. Rapid prototype is the second one. Then instead of waiting to build a complete system, we create a quick, simplified prototype. This helps in testing core features, identifying problems early, and refining requirements. Third one is ontology design and development. Ontology is about structuring knowledge into concepts and relationships. In this phase, we build the ontology for the agent so it can understand entities, roles, and connections in the chosen domain. Example, in education, ontology might link to the student to takes course taught by professor. Fourth one, a rule learning ontology refinement. Once the ontology is in place, the agent must learn rules and patterns. These rules can be learned automatically from data or refined based on expert input. Over time, the ontology is improved and updated to reflect the new knowledge. Hierarchical organization of the knowledge repository. Knowledge must be organized in a layered or hierarchical structure for efficiency. This helps the agent retrieve information quickly and apply reasoning without confusion. Example, organizing knowledge into categories like general knowledge, domain knowledge, task, and specific rules. The sixth one is a learning based design and development phases. Finally, the agent undergoes learning cycles where it improves the performance through the interaction with the environment. This phase ensures the agent is not static but continuously evolving to become more accurate and intelligent. The first step is an agent design and development using learning technology is requirement specification and domain understanding. In this phase, the knowledge engineer must clearly define what problem the agent is supposed to solve and what domain knowledge is required to solve it. Example, evaluating a PhD advisor. Suppose we want to build an agent that evaluates the hypothesis. John Doe would be a good PhD advisor for Bob Sharp. The agent should output a probability judgment like very likely along with clear reasoning for its decision. Research shows that choosing a PhD advisor is a complex decision making task. It involves multiple factors, publications, mentoring style, past student outcomes, advisors, availability, compatibility, and available resources. Role of the knowledge engineer. The knowledge engineer working with the subject matter experts like faculty members, researchers, and existing literature must carefully structure this domain knowledge. This knowledge is then encoded into the agent so it can evaluate hypotheses systematically. How the agent work. The learning agent takes a hypothesis such as John Doe is a good advisor. It then aggregates answers to a series of key questions. Does John Doe have strong publications? What is his mentoring style? How have his past students performed? Is there compatibility with the Bob research interest? Are sufficient resources available? Based on this structured evaluation, the agent computes a probability, example very likely, and presents the result with understandable reasoning. The image presents a flowchart chart illustrating the criteria for evaluating the quality of PhD advisor. The chart is structured as follows. PhD advisor quality criterion. This is the main category being evaluated. It has three sub-criteria. Professional reputation criterion. This criterion assesses the advisor's professional standing. It is further divided into four sub-criteria. Research funding criterion Q11 evaluates the advisor's ability to secure research funding. Research publications criterion Q2 assesses the advisor's research output and publication record. Citations criterion Q3 the measures the impact of the advisor's research through criteria citation count. Peer opinion criterion Q4 considers the opinions of peers regarding the advisor's professional reputation. Quality of student results criterion. This criterion evaluates the outcomes of the students advised by the PhD advisor. It is further divided into two sub-criteria. Publications with advisor criterion Q9 assesses the number and quality of publications co-authored by the advisor and the students. Employers of graduates criterion Q7 evaluates the career outcomes and employability of the advisor's graduates. Student learning experience criterion. This criterion focuses on the learning experience of students under the guidance of the PhD advisor. It is further divided into two sub-criteria. Research group status criteria and student opinion criterion Q5 and Q10. It assesses the status and reputations of the research group led by the advisor. Consider the opinions and feedback from students regarding their learning experience under the advisor. The diagram represents a reasoning process for deciding whether John Doe would be a good PhD advisor for Bob Shaw. Main hypothesis: John Doe would be a good PhD advisor for Bob Shaw. To check this, we need to evaluate the necessary conditions. Necessary conditions: research interest match. Bob Shaw must be interested in an area of expertise of John Doe. Here it says Bob is interested in artificial intelligence, which is one of John Doe areas. Condition satisfied. Then faculty availability. John Doe must stay on the faculty of George Mason University for the duration of Bob Shop's PhD dissertation. Condition satisfied. It says he will stay. Advisor quality. John Doe must meet PhD advisor quality criteria. PhD advisor quality criteria. The necessary qualities are broken down into three categories. The professional computation, reputation criterion. This includes having a research funding. John Doe satisfies this. Quality of student research criterion. John Doe's past students have done well. Student learning experience criterion. John Doe provides a good learning experience. Conclusion: since all three main conditions are met, research interest match, faculty availability match, then advisory quality also, all the subject criteria. Therefore, it is highly likely that John Doe would be a good PhD advisor for Bob Shaw. What is ontology in AI knowledge systems? Ontology is a structured way of representing knowledge. It defines concepts, entities, their relationships, and the rules connecting them. Example, in this case, Bob Shop, John Doe, and AI or entities and their relationships describe expertise and interest. The explanation of the diagram: the left side shows reasoning flow, while the right side converts into an ontology concept map. Reasoning side left starts with a statement: Bob Shop is interested in an area of expertise John Doe. Then checks: is Bob Shop interested in John Doe's expertise? Answer: yes, AI. Therefore, it is criterion Bob Shop interested in John Doe's experience. Ontology side, right side, converts this reasoning into the knowledge representation. Bob Shop is interested in AI. John Doe is expert in AI. AI instance of area expertise. Why ontology design is important? It removes ambiguity. Knowledge is clear and structures. Missions can reason automatically. Example: if Bob is interested in AI and John is expert in AI, John may be a suitable advisor. Ontology supports the reuse of knowledge across the different systems. It forms the basis of the semantic reasoning, intelligent search, and AI agents. The image presents a mind map illustrating the relationships between various concepts. Expertise. The central concept is area of expertise, which branches out into three subconcepts: mathematics, computer science, and biology. These subconcepts are further divided into more specific instances. Area of expertise, subconcept of mathematics, computer science, biology. Instance of AI, software engineering. Relationships: Bob Shaw is interested in AI. John Doe is an expert in AI. The image represents a flowchart designed to assess whether John Doe would be a suitable PhD advisor for Bob Shaw. The chart is structured as a decision tree comprising multiple boxes and arrows that guide the user through the series of questions and conditions. Initial question. The flowchart begins with the question: John Doe would be a good PhD advisor for Bob Shop. This inquiry is followed by a subsequent question: which are the necessary conditions. The necessary conditions for John Doe to be a good PhD advisor are outlined in points, three key points. Bob Shop should be interested in an area of expertise. John Doe. John Doe should stay on the faculty of George Mason University for the duration of PhD dissertation of Bob Shop. John Doe should possesses the qualities of good PhD advisor. Evaluation of condition. The flowchart then proceeds to evaluate each of these conditions through the series of questions and sub questions. For instance, it asks, is Bob Shop interested in the area of expertise of John Doe? And which is a professional reputation criteria. Learned rules. Throughout the flowchart, learned rules screenshots are displayed indicating that the chart is utilizing pre-existing knowledge or rules to inform its decision-making process. The image represents the flowchart illustrating the process of determining whether Bob Sharp is interested in an area of expertise of John Doe. The flowchart is divided into several sections, each representing a different step in a decision-making process. Initial question. The flowchart begins with the question, Bob Sharp is interested in an area expertise of John Doe? This is initial question sets the stage for the subsequent steps in the flowchart. Decision tree. The flowchart then branches out into a decision tree with the first decision being, is Bob Shop interested in an area of expertise of John Doe? If the answer is yes, AI, the flowchart proceeds to the next step. If the answer is not as AI, the flowchart does not provide the further information. Domain knowledge. The flowchart highlights the importance of domain knowledge in determining Bob Shop's interest. It references shared KB knowledge base, which contains evidence-based reasoning knowledge. The flowchart also mentions domain KB, a domain knowledge base, which includes a PhD advisor and insider threat as examples. Scenario knowledge. The flowchart further breaks down the knowledge into scenario KB, scenario knowledge base, which includes George Mason Union and University of Virginia as examples. This suggests the flowchart is considering specific scenarios or context in which Bob Shop's interested may be relevant. Is learning-based design and development phases. The problem identification is the first step. Identifying a problem that can be addressed using machine learning. This stage is critical as it sets the foundation for the entire project. It requires a deep understanding of issue and the potential benefits of applying machine learning techniques. Knowledge acquisition. Once the problem is identified, the next step is acquire relevant knowledge and data. This involves collecting and pre-processing data as well as the gathering the insights from domain experts. The quality and quantity of data acquired during this stage significantly impact the model's performance. Representation. After acquiring the necessary knowledge and data, the next step is to represent the information in a suitable format for the machine learning algorithm. This may involve feature engineering where relevant features are extracted from the data to facilitate learning. Effective representation is crucial for the model to learn meaningful patterns and relationships. Training. With the data represented appropriately, the model is then trained using a chosen algorithm. The training process involves adjusting the model's parameters to minimize the error between the predicted and actual output. The goal is to achieve balance between fitting the training data well and generalizing to unseen data. Inference. After training, the model is used to make predictions or inferences on new unseen data. This stage is where the model is applied to real world problems or tasks. The accuracy and reliability of the model inferences are critical for its practical utility. Evaluation. The performance for the model is evaluated using various metrics such as accuracy, precision, and recall. And F1 score evaluation helps us in understanding how well the model generalizes to new data and identifies the areas for improvements. It is an iterative process that may involve the refine the model or adjusting its parameter based on the evaluation results. Deployment. Once a model is deemed satisfactory, it is deployed in the appropriate environment. Deployment involves integrating the model into the applications or system where it will be used. Maintenance. This includes the monitoring its performance, updating it as necessary to adapt to changing conditions or new data, and ensuring it continues to meet required standards. Maintenance essentials to ensure the long-term effectiveness or relevance of the data model. Agent specification. This initial stage involves defining the requirements and characteristics of the agent. It serves as the foundation for the subsequent development process. Second one is rapid prototyping. In this stage, a preliminary version of the agent is created to test its functionality and identify the potential issues. The rapid prototyping phase allows for iterative refinement and improvement. Ontology development. Ontology development focuses on creating a structured framework for organizing knowledge and concepts relevant to the agent's domain. This stage is crucial for ensuring that the agent can effectively understand and process information. Rule learning and ontology refinement. During this phase, the agent learns rules and refines its ontology based on the data it has been trained on. The goal is to enhance the agent's decision-making capabilities and improve its overall performance. Agent use and personalization. Once the agent is developed, it is deployed and utilized in various applications. Personalization involves tailoring the agent's behavior to meet the specific needs and perform preferences of individual users. Agent optimization. The final stage involves continuously monitoring and optimizing the agent's performance to ensure it remains effective and efficient. This may involve updating the agent knowledge base, adjusting its parameter, or incorporate new features. The image presents a grid of 17 colorful boxes, each representing the one of the United Nations Sustainable Development Goals (SDGs). The SDGs are a set of global objectives aimed at achieving a more sustainable and equitable world by 2030. Here is a detailed breakdown of the image. Grid structure: 45 4 into 5 grid with some boxes slightly cut off the edges. Color scheme: each box a distinct color ranging from red, orange, yellow, and green, blue, and purple, creating with a visually appealing the diverse palette. SDG icons and text. It can be 17 SDGs, text corresponding to the one of the 17 SDGs. Okay, the icons are simple, effective, conveying the theme of each goal. SDG numbers 1 to 17 are the top left corner of the each box. Then the SDG titles are written in white text with the each box. Then the SDGs represent the images of first one is no poverty, and second one is zero hunger, and third one is good health and well-being. Fourth one is quality education. Gender equality is the fifth one. Sixth is clean water and sanitation. Seventh one is affordable and clean energy. Eight is decent work and an economic worth. Growth, industry, innovation, and infrastructure is the eighth one. Reduced inequality is the 9th one. Then sustainable cities and communities, the 10th one. Responsible consumption and production is the 11th one. Climate action is the 12th one. 13th one is the life below water, and 14th one is life land. Then peace, justice, and strong institutions, partnerships for the goals. The learning technology is mapped with the sustainable development goals. There are four. The first one is SDG quality education. Fourth one, then SDG innovation infrastructure. Ninth one, then SDG 10 reduced inequalities. 10, then SDG partnership 17. And here, the contributing several key areas of sustainable goals. It focuses on quality education, innovation, and educational technology, reducing inequalities through the accessibility and personalization, and forecasting the partnerships for the knowledge sharing and collaboration positions. It has a significant player in achieving these goals objectives, the global objectives. Thank you.